Welcome to Oddly Real. I'm Nem Stefanovic. One of the fundamental forces in our universe is the electric force. This force is responsible for most aspects of our daily lives, including the atomic structure of matter, chemical reactions, electricity, and even the nature of light. The electric force is an example of action at a distance. One charged particle separated in space from another feels the electric force from the other particle as a push or a pull. In fact, there is a condition that is induced in the space surrounding a charged particle, whether it is near other particles or not. This is what we call the electric field. The electric field is a vector field, meaning that each point in the space of the electric field has a magnitude and a direction. Electric fields are also additive, so the effects of the fields from nearby charges can be summed together to produce a total effect. The field also stores energy and has an energy density. In this episode, we will discuss charges and electric fields as well as their properties. We also look at real-world examples of the application of electric fields, such as microwave ovens for cooking and electrical shielding for sensitive electronic equipment and personal protection. The concept of charge in matter is foundational in our universe. Charges can be positive or negative, and they are quantized, meaning that they only come in discrete packets in nature, those being plus 2/3, minus 1/3, and minus 1 charge units. Electrons have the familiar minus 1 charge, while quarks, which are hidden within protons and neutrons, possess the other values. In fact, we can define charges more specifically. The standard SI unit for charge, which is called a Coulomb, equates to one electron charge being minus 1.6 times 10 to the power of negative 19 coulombs. Charge is so fundamental that it is always preserved in every kind of reaction. We call this the law of conservation of charge. For example, a uranium-238 nucleus can undergo nuclear decay to produce thorium-234 and an alpha particle. But when you count the positive charges in uranium-238 and the total positive charges in the thorium and alpha particle, the charges match. This is even true for matter and antimatter annihilation reactions. If you take an electron with charge minus 1 and annihilate it with a positron with charge plus 1, the result is gamma rays that possess zero charge. This matches the total charge before the annihilation, which is minus 1 plus 1 is equal to 0. Thus, you can see there's a core requirement in our universe that charge must always be preserved. Charged particles are also able to exert influence on other charged particles through action at a distance. Interestingly, two charged particles that are separated from each other in space can feel each other's presence as a push or a pull. In other words, they feel a force. There's an explicit formula that describes this force, which is called Coulomb's law. F is the force in newtons, Q1 and Q2 are the two charges in units of coulombs, separated at a distance, r, which is in meters, and K, which is equal to 8.99 times 10 to the power of 9 newtons meters squared per coulomb squared, is a constant. Charges Q1 and Q2 can be either positive or negative. Additionally, two like charges, both negative or both positive, would feel a repulsive force. If the two charges were opposites, like one positive and one negative, they would feel an attractive force. The magnitude of the force is given by the value F. The electric force is a long-range force. In this case, we can calculate the force between two particles separated by a distance r. The key takeaway from Coulomb's law is that the magnitude of the force is the multiple of both charges, but divided by the square of the distance. That means the strength of the force starts to fall off quickly as the particles separate further apart. Particles that are separated by 2 units of distance will see a reduction in force by a factor of 4. Particles 3 units apart will see a reduced force by a factor of 9. Of course, the opposite is true when charged particles get very close. they will tend to repel very strongly as that distance is reduced. Let's look at an example to get a sense of the strength of the electric force. Imagine a small copper coin that is neutral in charge with a mass of 3.11 grams. Each copper atom will be electrically neutral, containing 29 protons with positive charge and 29 electrons with negative charge. The small coin contains a total of positive charge equal to Q equal to 137,000 coulombs. This is also true of its negative charge as well. This value of charge is enormous. If you could strip the coin of its positive and negative charges into two separate segments and separate them by 100 meters, they would feel a force of approximately 2 times 10 to the power of 12 tons. If you put those two coins at the opposite ends of the Earth, they would still feel a 120-ton force of attraction between them. That's extraordinary. Another way to think about how a charged particle exerts an influence at a distance can be through a field. The space around a charged particle, Q1, is filled with this field. Another charge, Q2, at a distance r from Q1, feels a force due to the presence of the field. We say that the electric field E is defined as the amount of force per charge at that location, if a particle was there. So the force on Q2 is equal to Q2 times E. Notice that the field E is a vector field, meaning that every point in space is associated not just with the magnitude of E there, but a direction which would indicate the direction of the force. Is there actually an electric field in space, or is this just another way to work with the forces between particles? Things get more complicated when charges aren't just in a fixed location in space. If you move one of the charged particles, obviously the field will have to change. It turns out that the field does not change instantaneously. It takes time for the field to adjust to the new location of the charged particle. The time at which the change occurs happens at the speed of light. So in fact, there is something very real about the electric field. Additionally, when something changes over time, it means that it has a past with a memory of those past events. The state of the electric field at a point in time depends on the past states of the electric fields from the other contributing sources. Think about the situation where there are multiple charges and they are changing over time. In this case, the various states of those charges will all play a role in influencing how the electric field will behave in the future in very complicated ways. One very important aspect of electric fields is that they obey the principle of superposition. This means that if there are many field sources, then the total electric field at any point in space is determined by the sum of the fields at that point from each of those sources. This turns out to be very useful for calculating the effects of electric fields when there are complicated charge distributions. We can explore the electric field distributions for some common charge distributions. For example, imagine a ring with an equal charge distribution around it. If you look in the center of the ring, you will notice that the contribution of an electric field of any component around the ring has an equal but opposite contributing electric field from the other side. That cancels it out. This is true all around the ring. So the electric field in the middle is zero. Additionally, if we stay on the axis going through the center, but moving away from the ring, we see that the further we travel away, the smaller the ring looks, and the more it behaves like a charged point and not a ring. In another example, let's look at a very long rod that has an equal charge distribution along its length. In this case, we get the interesting result that the electric field strength no longer falls off by r to the power of 2 with distance, but only r with distance. The presence of a charge distribution along a whole length, which is one dimension in space, has yielded an electric field that is stronger further out in space. We can also look at a similar example, but with the electric field strength along a very large non-conducting sheet of charge with an equal charge distribution across its surface. In this case, you get the interesting result that the electric field strength no longer diminishes with distance at all. It is a constant. Keep in mind, this is assuming an idealized circumstance that this sheet is extremely large and we are close to the sheet. Alternatively, this also works if the sheet is not extremely large, but we are extremely close to the sheet and away from its edges. There are also shell theorems that describe the force effects on charges within and outside of a charge distribution. First, if a charged particle is outside of a shell of equal charge distribution, the charged shell acts as if all of its charge was concentrated at its center. In other words, you can treat the charged shell equivalently as a point charge at its center with all of the shell's charge concentrated there. Second, if a charged particle is inside a shell of equal charge distribution, the charged particle experiences no electric force. The sum of the contributing electric fields from the shell charges at each point in space in the interior cancel out. Additionally, we can also examine what happens to an isolated conductor with an excess charge added to it. In this situation, the charge particles will repel each other and quickly distribute themselves around the surface of the conductor. There is no charge within the conductor interior. Additionally, depending on the shape of the conductor, the charges will not necessarily be equal in their distribution, and the charge density, or charge per unit area, will vary from place to place. The distribution would happen in a way to ensure that the electric field in the interior of the conductor was zero. If this didn't happen, then there would be forces on the charges causing them to move around and generate currents, which does not happen. Currents in isolated charge conductors with excess charge can happen at first before the charges have redistributed themselves, but then there will be no currents once the charges settle. What happens if there is a cavity within the conductor body? Would it be possible to have charges distributed along the walls in the interior? The answer is still no. Outside of the conducting surface, the external electric field will always point perpendicular at all of the points on the surface. If this was not the case, then there'd be an electric field component along the surface horizontally, which would result in forces on the surface charges to produce current. Again, this does not happen. Let's look at an example involving electric shielding. If you take an uncharged conductor, like a metal body, and place it in an electric field, you'll see the charges on the conductor redistribute themselves to make the electric field within the interior go to zero. The electric field will be perpendicular at all points along the surface of the conductor. The shape of the body will dictate how the charges redistribute themselves, and the charge density will not be equal at various points on the surface. If there are sharp edges, there could be a large charge distribution there, which could cause the air around it to ionize and produce a corona discharge. This type of situation is very dangerous when there is a threat of lightning strikes. It turns out that the electrical breakdown voltage for air is 3 kilovolts per millimeter, which causes the air itself to start conducting currents. Ideally, the best protection for this situation is to be within a cavity within a conducting shell, which has an electric field equal to zero. A car serves as excellent protection from lightning strikes. This is also the same principle used by Faraday cages to protect sensitive instruments from electric fields. Let's look at an example of the application of electric fields for useful work, such as microwave cooking. Water molecules are naturally polarized, meaning that they have unequal charge distributions, where one side is more positive and the other is more negative. This makes water molecules very sticky, and they tend to group themselves together in pairs or triples because of that electrical attraction. When water molecules group together, some energy is transferred to their molecular motion as well as to the surrounding molecules. Alternatively, molecular collisions result in the opposite effect, using energy to break up the groups, which removes some of the energy of motion. Overall, the temperature of water stays the same, as some groups of water molecules will form while others break up in equal balance on average. However, a microwave produces a rapidly oscillating electric field. This field influences the water molecules by applying a torque or twisting force to break up some of the triple groups. The energy used to break them up comes from the electric field supplied by the microwave. Now these broken up molecules can regroup with other molecules to release some of that energy into molecular motion. This process continues with more and more of the microwave energy being added to the molecular motion, thereby increasing the water temperature. Since food has water in it, this process works well to warm up foods. If water molecules were not polarized, this process would not work. One very fundamental electrical device used in many electronic circuits is called a capacitor. This device is used to store energy in the form of an electric field. Unlike other energy storage devices like batteries, capacitors are not meant for long-term storage. They also have many other uses beyond just energy storage as well, such as signal filtering and maintaining power stability. We will look at a very simple example of a capacitor, which is called a parallel plate capacitor. It consists of two conducting plates in parallel to each other. When you apply a charge to the plates, such as plus Q on one and minus Q on the other, this sets up an electric field between the plates. In between the plates, the field is very uniform or similar throughout. However, there is a little field fringing on the edges of the plates where the plates end. There's a relationship between the amount of charge on the capacitor plates, Q, and the voltage applied across the plates, which is Q is equal to CV. C is what we call the capacitance, and it's a measure of how much charge needs to be added to the plates to produce a certain voltage, or alternatively, how much charge can be stored within the capacitor for a certain applied voltage. It takes work or energy to charge up a capacitor. You can imagine taking one electron from one plate and moving it over to the other one at a time. As the charges build up, an electric field also builds up between the plates, which resists additional charge transfers. This means you have to do additional work for every added electron you move. In the real world, this charge buildup happens by a battery or other energy source that applies a voltage across the capacitor, which moves the charges through a wire. The work is done by chemical energy supplied from a battery, for example. But where does this energy go once it is put into the charges within the capacitor? The energy is in the form of potential energy, and it's used to build up the arrangement of the charges on the plates of the capacitor. This also has resulted in a buildup of an electric field between the plates. It turns out that if you took two capacitors, C1 and C2, both with the same plates, but C1 had twice the plate separation compared to C2, then all things being equal, the only difference is C1 has double the volume between its plates. If both have the same charge, Q, on their plates, it turns out that C1 will have twice the stored energy. So two capacitors with the same charges yield the same electric fields, but C1 has twice the volume and twice the energy. Thus, you can think of the energy of a capacitor as being stored in the electric field itself. In fact, the electric field has an energy density, or energy per unit volume, between the plates. A parallel plate capacitor, excluding the fringing on the ends, has a uniform energy density between the plates. The energy density is proportional to the square of the electric field magnitude, E. Any space between the plates where there's an electric field contains energy. In fact, this concept of energy stored in an electric field is valid for any electric field, not just parallel plate capacitors. Can we release the energy stored in the capacitor somehow? The answer is yes. For example, if you have a charged capacitor, you can close a switch or make a circuit connection to link one plate to the other via a conductive path, which will cause the charges to redistribute themselves back to neutralize each other. The moving charges produce a current which converts the electrical field potential energy into the kinetic energy, or energy of motion, of the moving charges. A note of caution here: this discharge can happen very quickly and generate a lot of current if there isn't enough resistance in the conductive path. This can cause burns or electrocutions. Even for small capacitors, if a capacitor is discharged too quickly. So don't try this on your own. In fact, controlled capacitor discharges are what are used to make medical defibrillators to help stabilize victims of heart attacks. Ultimately, the capacitor will be left discharged and the electric field will be zero if fully discharged. Some of you may have noticed that Coulomb's law for electric force looks very similar to the equation describing the force of gravity. F is equal to G times m1 times m2 divided by r to the power of 2, where F is the force of gravity, m1 and m2 are two masses, and r is the separating distance in space between the two masses. And here G is the gravitational constant, 6.67 times 10 to the power of minus 11 newtons meters squared per kilogram squared. Both forces reduce by the square of the distance between the particles as distance increases. Many of the results that we have shown here for charge distributions and shell laws also apply to mass distributions too. Additionally, the force of gravity also obeys the principle of superposition as well, at least when the Newtonian laws of gravity apply. There are some differences that are worth noting. Gravity is only an attractive force, whereas the electric force can be either attractive or repulsive. Strangely, there is enormous difference in their relative strengths. For example, take two electrons. We can compare their electric force of repulsion to their gravitational force of attraction between their masses. And we get that the gravitational force relative to the electrical force is equal to 1 divided by 4.17 times 10 to the power of 42. This ratio does not depend on distance. It's a fundamental constant of nature. The difference in strength is enormous, with the electrical force being much, much larger. This number is a clue to a universal equation for nature. If we were ever to develop a model for the unification of all physical forces together, this constant would somehow be a part of it. Finally, it's also worth mentioning that electric fields can be created without any charges at all. It turns out that they can also be produced by a changing magnetic field anywhere in space. In fact, that's actually how light propagates as a wave. It consists of oscillating electric and magnetic fields that are coupled together. There's a lot more than we can discuss about the nature of electric fields, but we'll have to leave it here for now. I hope you enjoyed this episode, and remember, oddly real, really interesting.